Today we are diving into an incredible thought experiment from the mind of Richard Feynman. It's a story about a simple little disk that seems to put two of the most fundamental laws of physics on a collision course, and it looks like one of them is about to break.
And that's really the question at the heart of all this. It makes you wonder, what happens when our understanding of the universe completely contradicts itself? Could a law that we've trusted for centuries actually be wrong?
You know, the really beautiful thing about Feynman's paradox is that it all starts with something you could almost build yourself. There are no black holes, no bizarre quantum effects, just a couple of very simple parts.
Okay, so picture this. You've got a plastic disc, and it's totally free to spin. Around the edge, we've attached a bunch of tiny metal balls, and they all have an electric charge. Right in the middle, there's a coil of wire, a solenoid, and we've got a steady current running through it, which creates a magnetic field. But here's the key. At the very beginning, nothing is moving. The whole setup is completely still.
And this is where the trouble starts. It's like two heavyweights of physics step into the ring, and they predict completely opposite things. On one side, you have the law of conservation of angular momentum, which says the disk absolutely cannot move. But on the other side, Faraday's law of induction says the disk has to rotate. They can't both be right. Or can they?
So let's start with the reigning champion, the law that governs everything from spinning galaxies down to figure skaters, the conservation of angular momentum.
Simply put, angular momentum is just the rotational version of regular momentum. You know how a figure skater pulls their arms in to spin faster? Their total angular momentum actually stays the same. The unbreakable rule is this: in a closed system, you can't just create or destroy angular momentum. It has to be conserved.
So, what's the total angular momentum of our little system at the very beginning? Well, since nothing is rotating, the disk is still, the charges are still, the angular momentum is a big, fat zero. And according to that law of conservation, if you start with zero, you have to end with zero. There's no outside force pushing on it. So, from this point of view, the disk should never, ever move. It really seems like an open and shut case.
But then, the challenger steps into the ring, a true giant of electromagnetism, Faraday's law of induction, and it predicts something completely different.
Okay, so what happens if we suddenly switch off the current in that coil? Well, it kicks off this five-step chain reaction. The current stops. That makes the magnetic field collapse. Now, Faraday's law tells us that a changing magnetic field creates a circular electric field. That new electric field then pushes on all those little charges around the rim, creating a torque, and boom, the disk starts to spin.
And the physics behind that push is right here in this equation. Now don't worry about all the symbols. The main idea is actually pretty simple. That E on the left is the electric push. Everything on the right just represents the magnetic field changing over time. So this is really just the universe's way of saying a changing magnetic field must create an electric push. It's a fundamental rule.
So now we're stuck with this undeniable paradox. One law says the disk cannot move. Another law, backed up by some very solid math, says it must move. If the system starts with zero angular momentum and ends up spinning, where in the world did that new momentum come from? Did we just break one of the most sacred laws in all of physics?
Well, the solution is just as elegant as the paradox itself, and it turns out the answer was there the whole time, stored invisibly right there in the empty space around the disk.
You know, Feynman himself described the solution in this amazing way. He called it a mystic circulating flow of energy, and he even admitted that at first it just seemed ridiculous. But he realized it was absolutely necessary to make the universe work correctly. There's a real momentum flow, even when nothing appears to be moving.
So the solution lies in this thing called the Poynting vector. And really, all it means is this. Whenever you have an electric field and a magnetic field existing in the same space, like we do here, with the field from the charges pointing out and the field from the coil pointing up, momentum gets stored in the empty space where they overlap. It's like an invisible circulating energy.
And this isn't just some vague idea. Physicists can calculate this hidden momentum with incredible precision. This equation might look a little intense, but its job is simple. It just adds up all the tiny bits of momentum that are stored where the electric and magnetic fields cross over. And it gives us one total number for all that hidden angular momentum.
And that is the big reveal. Our initial assumption was wrong all along. The total angular momentum of the system was never zero to begin with. We only counted the physical, mechanical momentum of the parts, but we totally forgot to count the momentum stored in the electromagnetic field itself. It was there the whole time, hiding in plain sight.
So with this new piece of the puzzle, we can go back and see how our laws of physics aren't broken at all. In fact, our understanding of them actually gets a whole lot deeper.
So when we turn off the current, all that hidden momentum in the field can't just disappear. It has to go somewhere. As the field collapses, its angular momentum is perfectly transferred to the physical disk, and that's what makes it spin. The momentum just changes its form, from field momentum to mechanical momentum. Nothing was created out of thin air.
And you can almost hear the sigh of relief in how one physicist put it after working through all the math. The final spin of the disk perfectly matches the amount of momentum that was initially stored in the field. Phew, the conservation law is safe after all.
So what's the big takeaway here? Well, first, that momentum isn't just something for moving objects. Fields themselves can have it too. Second, even totally static, non-moving fields can contain this hidden, circulating angular momentum. And maybe most importantly, the law of conservation of angular momentum is even more powerful than we thought. It always holds true. You just have to remember to count everything.
And that leaves us with one last, really fascinating question. Feynman's paradox shows us that what we think of as empty space is anything but. It's this dynamic place that can store both energy and momentum. It really makes you wonder, what other incredible secrets are still hiding out there in the vacuum, just waiting for us to find them?